Now that we have an understanding of vibrations, we can use our understanding of vibrations to talk about wave motion more generally. And when we talk about the motion of a wave, it's actually not that each particle in the wave is transferring all the way down the line. What we're actually seeing is a transfer of energy on the way down the line. But each individual particle only vibrates. It only moves in one direction and then returns to its original position. So for example, in the transverse waves we looked at in our previous note, for a transverse wave, we might see the energy of the wave moving from left to right. And so we would see the wave crests moving from left to right. But each individual particle in the wave is actually just vibrating up and down. But because it's doing it in a particular pattern, it creates the appearance of energy moving through the wave from left to right. But it's just the energy, not the particles themselves. With that in mind, we can also talk about another important definition. And it's one that we didn't talk about in our previous note. Some of the things from our previous note, like amplitude and period and frequency, are all things that we're going to see also apply to waves. But we can talk about one new factor as well, which is called the wavelength. And the wavelength is just the length of one cycle of the wave. So as long as we can trace out what the path of that wave is doing through one complete cycle, if we measure that length, we know its wavelength. So what we're trying to do is measure the distance between any two identical points in the cycle. So one thing I've suggested is, for example, the top of two crests or the bottom of two troughs. And just to clarify what that means, this area in the picture that you see, whenever you are above your rest axis, we tend to call that part of a wave a crest, and we tend to call the part below the rest axis the trough. So what we're trying to do is trace out one full wavelength. And one suggestion I give is the top of two crests. So for example, if I have one crest and the top of it is here, I trace out the path all the way down and all the way back up, and that brings me back up to the top of a crest again. That's following it through one complete wave cycle. And then if I measure that distance across, I get one full wavelength. And when we actually write down the symbol for wavelength, we use the Greek letter lambda. It's called lambda, but it actually looks like an upside down Y. So that's the letter that we're going to use to represent wavelength. But I didn't have to measure it from one crest to another, as long as I trace out one full wavelength. So another option would be to start at a trough. So if I start down at the bottom at the trough, I go all the way up and then come all the way back down, and I end on a trough as well. If I measure the distance from a trough to a trough, that's also one full complete wavelength. I can even go a bit further and say it doesn't have to just be a crest or a trough. So if I just pick a random point on my wave, let's say right about here, as long as I go all the way up, come all the way back down, and then up to the same level in the wave, I have traced out one complete wavelength as well. So if I measure that distance across, that would also be one full lambda. And there's even one other option you could look at, and start from the actual rest axis. So if I start from the rest axis, we just have to be extra careful. So we can go all the way up and then come back down to the rest axis, but that would only be half of the wave cycle, because the wave does continue on all the way down and then back up to the rest axis. So you need to make sure you're following through the full cycle of the wave, all the way up, all the way back down, and then back to your original spot. All of those, though, if we measure the distance horizontally straight across, that would tell us the length of lambda, the length that we call the wavelength. Now, from there, with that in our back pockets, we can actually talk about a new property of the wave, talk about its velocity. And so really what we're talking about is how quickly each pulse, each crest, if you want to think of it that way, is moving for the wave. And that pulse has a certain speed that it's moving with, and it's also traveling in a particular direction. So if you have a speed in a direction, it's giving you a velocity. Now, each wave may move at a different speed depending on what substance the wave is moving through. So for example, sound waves need something called a medium. They need to move through particles, for example, air particles or water particles, or maybe solid particles like steel. And a sound wave transfers its energy through that medium. But if it's transferring through air, it may transfer at a different speed than if it's going through water or if it's going through steel. Those all have different speeds of sound because each individual substance provides a different medium to transfer that energy. But if we do know some things about the wave, we can figure out what speed waves might move. And it's using something called the universal wave equation. So in general, if we want to find the velocity of a wave, what we can do is focus in on just one particular cycle in the wave. Now, keep in mind, we're trying to find a velocity. And in this case, we're going to make the assumption, which will be true in this case, that the velocity is constant. So in the end, we're going to use that special formula that v is equal to d over t. Velocity is equal to displacement over time. But if we focus in on one cycle, we can be a little bit more specific. So if we think about what displacement is equal to, well, how far does a wave travel in just one cycle? It travels lambda. It travels one wavelength. That's what wavelength means. The distance that is covered in one cycle, or the length that is gone through in one cycle. And then we divide by the time it takes. Well, the time it takes for one cycle to be completed, we actually have a special name for that. That special kind of time, we give a capital T, and we call that period. So really, if we're looking for velocity, what we're actually doing is taking lambda, the wavelength, and dividing by the period. In other words, we're saying the displacement in one cycle divided by the time for one cycle. So really what we're seeing is that the velocity in our particular case is lambda, the wavelength, divided by the period. But typically we don't actually use that as our main wave equation to find velocity, because we often don't know what the period is. It's a lot more common that we're told what the frequency is. But we can work with this a little bit. So if we are doing lambda divided by t, well, dividing by something is the same as multiplying by its reciprocal. So for example, dividing something by 2 is the same as multiplying by 1 over 2, because 1 over 2, or 1/2, is the reciprocal of 2. So instead of dividing by period, dividing by big T, I'm going to multiply by the reciprocal. So if I take that lambda that I had on top, and instead of dividing it by t, if I multiply it by 1 over t, I accomplish the exact same thing. But we talked in our previous note about what 1 over t is actually equal to. It's the frequency. So the other way we could state this is frequency multiplied by lambda. And so just to really pull this out and hammer it home, what we're seeing now is that in general, the velocity of a wave we can always find if we take its frequency that we can often find and multiply by its wavelength. And that, specifically v equaling f lambda, that is the universal wave equation. And it's an incredibly important piece of information to know when we are trying to find unknown things related to waves. To give you an example of that, we can go through example 1. So if we know that water waves are traveling at 1 meter per second, and we know their frequency, can we find their wavelength? So this is just a simple case of givens and requireds. We know that the velocity of these water waves is 1.0 meters per second, and we know that the frequency is 0.50 hertz. We are trying to find the wavelength, so we are trying to find lambda. Always start with the formula that we know, so velocity is equal to frequency times lambda, so v equals f lambda. But if we want to get the wavelength, we can divide both sides by frequency. So if we get lambda all by itself, the only way we could do that is by taking velocity and dividing by frequency. So when we do that, we can plug in what we know. It's 1.0 meters per second divided by 0.50 hertz. When we do all of that, we get 2.0, and that would be in meters. We'll talk a little bit more in class about how the units interact and why exactly we get meters, but logically we should know that our answer is in meters because it's a length, and meters per second was the unit that was used for velocity. So we end up with our answer in meters, meaning that if you measured the distance from the top of one crest of that water wave to the next crest of the next water wave, it would be a distance of 2 meters apart. That's what we found by finding the wavelength.